Hello, this is Glenn Michael Pei, and my presentation is about liquid crystal display, or LCD. What is an LCD? A liquid crystal display is a flat panel display that uses polarizers, liquid crystal, glass plates, electrodes, and backlight. Figure 1 is an LCD monitor, and Figure 2 is the LCD display module. The structure of an LCD consists of a light source, polarizer, glass plate, electrode, and liquid crystal. The liquid crystal is enclosed between two glass plates. This configuration is called the twisting nematic liquid crystal display, or TN-LCD. Figure 3 is a diagram of a TN-LCD system. One of the main components of TN-LCD are the polarizers. They are used to filter light, only letting light of a specific polarization pass through. If an unpolarized light passes through a polarizer, its intensity is halved. As seen in Figure 4, the oscillating wave is the light's electric field. The vertical light passes through the horizontal wire grating, while the horizontal light gets absorbed. If we have two polarizers and situated in different angles, it follows Malice's law, which states that the intensity ratio is the cosine squared of the angle. In Figure 5, we can see the variation of intensity ratio with the angle of rotation of the polarizers. If the two polarizers have no angle of rotation, the light does not lose intensity. But if the light has 90-degree rotation, it will lose its intensity. On the right, Figure 6 shows that there is no light passing through a 90-degree polarizer. The next key component of a TN-LCD is the liquid crystal. It was first discovered by Friedrich Renitzer, which is a gentleman in Figure 7. He was a botanist who was analyzing the role of cholesterols in plants. As he inspected the substance called cholesterol benzoate, he found a peculiar behavior. Right after the substance melts, the liquid is cloudy, but as the substance is heated up more, the color of the liquid becomes clear. In Figure 8, we can see the two distinct phases. He named the cloudy phase of the liquid crystal phase. In the molecular scale, liquid crystal has three distinct phases, which is the nematic, smectic, and cholesteric phase in increasing molecular order. What the molecular order defines is its degrees of freedom. We can see that the nematic phase is not bound by layers. Smectic is not bound by being in the same orientation as its layers. The molecular order of the crystal varies with the temperature. If the temperature is increased, the liquid crystal behaves more like the nematic phase, and if the temperature is decreased, it behaves more like the cholesteric phase. The liquid crystal phase present in a TN-LCD is the nematic phase. A unique property of liquid crystal is its anisotropy. It has different properties in different orientation. We identify the properties in relation to the director n-hat. Figure 10 depicts the director direction relative to the orientation of the liquid crystal. The properties of the liquid crystal that is parallel to the director is different to the perpendicular properties. The two most important anisotropic properties of a liquid crystal is its refractive index and dielectric permittivity. We will talk more about the properties in the next slide. What is the refractive index? The refractive index is the ratio of the velocity of light through a vacuum and through a medium. This is given by n is equal to c over v. We can quantify this using the Snell's law. And Snell's law is n sine theta 1 is equal to n2 sine theta 2. And essentially what we do is we have light passing through two different mediums. Let's say the liquid crystal and air. Now the n of air is 1 while the liquid crystal is unknown. So we shoot light at an angle and we can find the refractive index of the liquid crystal. But liquid crystals are kind of different, as that liquid crystal has two different refractive index, one that's parallel and one that's perpendicular to the director n-hat. Now we can see on the figure 12 is a birefringence of a calcite. It shows two different refractive index. As you can see, there's one that's being bent more and there's one kind of bent, and there's one that's through light without passing through a medium. Now, because the light has two different velocities, this actually acts like a polarizer. One light that's slower, and one light that is faster. And these are called the ordinary waves and the extraordinary waves, which has the refractive index of N0 and Ne. We can quantify the birefringence by subtracting the extraordinary wave and the ordinary wave. As you can see here at figure 13, at A, it's when it's the light propagating is parallel to the director, or is actually not at the same axis as the director. And while the extraordinary wave is the wave that's vibrating along the optical axis, which is the director. Because there's two different waves, this actually makes liquid crystal become a polarizer, as it separates the extraordinary waves, which is vibrating at one orientation, and extraordinary waves, which vibrates on the other orientation. Because the birefringence of an LCD is essentially a polarizer, we assemble the TN LCD where the polarizers are at 90 degrees and the liquid crystal is oriented in a helical structure. Now what this does is essentially it's a bunch of different polarizers repeatedly at really small angle. And if you remember Malice's law, if we have angles of close to zero, we can essentially we can keep most of the intensity of the light. And if we have like almost infinite of these, because the liquid crystal is a liquid, it's continuous, then we could transmit light through that. Now, we can make it into a helical structure by applying some surface anchoring into the glass plate. And we actually, if you look at figure 14, the orientation of the end director is at 90 degrees of each other, and that's how we make a helical structure in the TN LCD. Now, because liquid crystals act like a polarizer, we can make it as if it's a lot of polarizers when you rotate into helical shape. Now, because we rotate it 90 degrees, we can actually find, like, kind of give a sense of how much light is passing through. Now we can see here that the intensity ratio of the transmitted light is given by I over I0 is equal to cosine squared times n of total angle divided by n, where n is the number of polarizers. Now liquid crystals are a continuum. Therefore, if we have a rotation of 90 degrees, there's essentially infinite amount of polarizers. So the amount of intensity given off by the liquid crystal rotated 90 is essentially 1. But this is not always true, as it's not really infinite, as there's like it's based on the thickness of the liquid crystal. But it's safe assumption that it's at least bigger than 100 polarizers. And 100 polarizers is way above 90%. So I've made a small exercise with birefringence because I thought it was very interesting. So a key component of birefringence is that it has two different index of refractions, one for extraordinary and one for ordinary waves. Now because of this, there's gonna be a difference in phases between the two rays, and we could actually use liquid crystals to make the to make it to have two lights have a phase difference. Like it's called light wave retardation. And the scenario here is we shine a light of unpolarized light, and then the ordinary waves will have will pass through the medium, and it will be like slowed down but not slowed too much, and the extraordinary wave, which is NE, will have a higher refractive index, and it will pass through the material slower. And we are trying to find the phase difference between each of the wave, like how much has it slowed down compared to like how much the ordinary wave slows down compared to the extraordinary waves. So here we have the range equation, which is v times t, and then we can apply it to the diagram, which is the liquid. Um, for the velocity e, the time it takes to pass through the medium would be L over V, which is given by those two equations. So now the difference between the time that it takes between the extraordinary ordinary will give you the time it takes that the light has been passing through air without being in a medium. So like while extraordinary waves are still in the medium, and now we could find using we could substitute it to delta t, and then we could substitute the definition of refractive index, and we get L over C delta N. Now C times delta T will give you the difference between the lengths of the wavelength, and now we could just substitute it in, and then we could find delta L. But delta L over lambda will give you the ratio of shift of wavelength. So now, in order to make it a degrees, we can make it a delta L over lambda times 2 pi, which gives you phi, which is equal to 2 pi L delta N over lambda. And this is actually used in like this used for wave retardation in optical physics. So the dielectric anisotropy actually measures the response of the material to an applied electric field. So what it has is if the dielectric permittivity parallel subtracted by the perpendicular will give you the dielectric anisotropy, and this indicates what orientation of the molecules would be if there's an applied electric field. Now, if you see on Figure 17, if the electric anisotropy is positive, then the molecules actually line parallel to the electric field, while if it's negative, it rises perpendicular. Because of the dielectric anisotropy, if we apply an electric field, the the crystal director actually aligns itself with the electric field, and then the birefringence actually varies with respect to the angle. And then what this states essentially is that if the angle of the director is becomes really small, like the theta in figure 18, then it actually just becomes ordinary waves. Therefore, both of the incoming waves become ordinary waves. And it's not gonna show any more birefringence and not gonna polarize the light. And this actually is useful in terms of TN-LCDs, as we have to be able to either rotate the light or not rotate the light. So this is the list of liquid crystals, like where Tm is the melting point, and Tc is the cleaning temperature. Delta E is the dielectric anisotropy, and delta N is the birefringence. You can see the value here is that delta N actually varies kind of closely into delta E, delta epsilon, and you can see it from the values. They're fairly close. If the delta N increases, so does the delta E. So we laid the foundation of LCDs. First, the liquid crystal has the birefringence, the dielectric anisotropy, and the surface anchoring. These are these help the LCDs. Birefringence helps it for rotating, which is waveguiding. Dielectric anisotropy orients the molecule into vertical or horizontal, depending on if there's an applied voltage or not. Surface anchoring makes sure that it's at 90 degrees, making that helical shape. An electrode creates the electric field, and the polarizers ensures that there's light. It analyzes if there's light passing through or not. On the right side is the exploded view of the TN-LCD. We can see here that the liquid crystal, if you actually do not apply any voltage, light passes through, as the light actually gets wave guided by the liquid crystal, making it rotate a 90 degree. And from previous example, we actually do not lose a lot of intensity by doing this. And if we turn on the voltage, it makes it align vertically. And what this does is that the birefringence of light becomes the same value, as both of them becomes ordinary light, ordinary wave. Therefore, the light doesn't really get turned, and from the 90-degree polarizers, it actually outputs a dark light. I mean, no light. While if the voltage is off, it has it outputs a light. Now, the transmitted light across the liquid crystals can be controlled by applying a voltage. The applied voltage has this um, voltage threshold, but then as soon as you pass the voltage threshold, the transmission of light becomes sensitive with the increase of voltage, where as you increase the voltage, it lowers the transmission. So when in an LCD, if you increase the voltage across the electrodes, then the light becomes darker, as seen from the previous diagram. Now, in computer languages, we can control this assignment by assigning different transmission levels. So if the value of the transmission is 255, then all the light passes through, and if the value is 0, then there's no light passing through. Now everything between that would be different transmissions. So for an LCD monitor, we have different we have each pixel being controlled by 3 different subpixels, and each of them is red, green, and blue. Each pixel has one red, one green, one blue, and each are controlled by an LCD mechanism, which is we could actually change the voltage applied to each subpixel, and we could control the light transmission for each subpixel. Now we could change the brightness of the subpixel, then we could actually mix and create different colors. And each of the color present in the screen is actually a mixture of red, green, and blue. And in white light is actually 255, 255, and 255. And we can see in figure 22 is that this is the mixture of different values of light. If say you're at 0, 0, 255, it means that you're at blue. Now if you have 255, 255, and 0, it means you're at yellow. It's different types of mixture, and if You have if you lower the value, then you have different types of colors. And that concludes my presentation. Thank you.